Hi, I'm Rosa, and I'm currently working at NGI as a researcher. And the presentation I'm going to do now is about part of my PhD thesis that I did before coming to NGI to be a postdoc before now, 3 years ago. And, and it's about a landslide early warning system use of hydrometeorological thresholds. So yeah, it's a result from my thesis that I did at UPC in Barcelona, but that I'm presenting now from NGI. And also everything that I will be presenting, it's published in a paper. So if you are interested, you can also go and check and learn more about it. So, okay. So as we know, landslides are an important hazard that affect areas in mountains in the world. And even though it's not as known in Spain to be a hazard, we still have some landslides. And also because of climate change, we see that we have them with a higher frequency, and they also impact infrastructures and buildings, and they represent yeah, issues for population that live in the areas that are affected by them. So what we need to do and what we want to do is to create ways of decreasing the risk, and we need those tools to decrease the risk, and so that emergency managers and people that live in the areas that might be affected can be aware of the hazard and take actions. So the landslide early warning system for Catalonia, this is what I developed during my PhD thesis, uses radar rainfall information as an input. Then it computes the hazard in the warning on a subbasal level. And if you are interested, you can zoom in because the warning levels are actually computed on a 30-meter pixels. So you can zoom in into the area you're interested and observe what's going on. And here you have some results of the landslide warning system working for an extreme event that occurred in Catalonia in January 2020, where multiple landslides were triggered. And as you can see, we get that this warning level increases in the areas that are affected by more precipitation. Yep. So as I said, the original version of this landslide early warning system used only radar rainfall observations to compute the warnings over Catalonia. But what we want to do, what a problem is that soil moisture is very important, and we know, but mostly it's not taking into account into regional scale landslide early warning systems. So what we did was combining susceptibility and rainfall and obtained a warning map. But what we thought is, can we improve the landslide early warning system performance if we, instead of using only rainfall information, use also information regarding soil moisture? So what we did was including soil moisture as an additional input. And then instead of using rainfall thresholds, as we had been using before, we replaced them by hydrometeorological thresholds that combine rainfall and soil moisture information. Then we obtained the hydrometeorological hazard over the entire Catalonia. And then that was the thing that was combined with susceptibility to obtain a warning map that would be updated every time we got new rainfall and soil moisture information. So when we started this to work on that, we thought, okay, we need soil moisture data over all Catalonia. And that was a challenge because if you can see in this map, and that's the soil moisture sensor network existing in Catalonia. And it's only a few sensors located in the northwest. And we know that this is not good enough for the entire region because the soil moisture that those sensors would measure up there in the northwestern Pyrenees is not representative of what's the soil moisture over all Catalonia. So we decided that this was not the best option for our case. Another option would have been using satellite soil moisture information, and we considered that, but we also thought that, okay, we want to run this landslide early warning system. This is running operationally in real time. So what we need is to have this information in real time. And the case with satellite products is that most often they come with some time latency. So you don't have the soil moisture the day that the soil moisture is observed, but you have it a few days after. And this is not interesting for us, which we wanted to have this on real time operational. So instead of satellite, we decided that our way to go would be using the output of hydrological models, which we have distributed hydrological models covering the area. And we decided to use the list flood model, and we used the runs from the EFAS, which is the European Flood Forecasting System. So we have this soil volumetric water content, which is modeled by list flood, covering all Europe. And then we have daily outputs, and they have a 5-kilometer resolution. And here in these two maps, you can see the volumetric water content over Catalonia to 2 days. No, it's the same day. Okay, the same day. And we can see that we have a spatial variation of the soil moisture in areas in the north and in the south, with areas with more moisture, volumetric water content than others. Yep. Then we analyzed this, and here we see that over time, for a period from 2018 to 2020, and here we have the percentiles of volumetric water content conditions in Catalonia. So in the left, you can see the 25th percentile, and in the right, you can see the 75th percentile. As you can see, the areas that are more that have higher soil moisture are located in the Pyrenees, and they are usually areas where it rains more, and so they are more wet. And towards the southwest, we have areas which are a bit more dry, and therefore it's lower water content on the soil. So after analyzing all this, we decided to obtain these hydrometeorological thresholds. So what we thought is, okay, we will include volumetric water content as a third dimension into the intensity duration space. So here we can see the intensity duration thresholds that the landslide early warning system was using. And what we did is include a third axis, which would be volumetric water content. So then if we look at this volumetric water content, we could summarize it for the intensity duration for the given duration, like in for the equivalent intensity given a duration. So here we have the equivalent intensity volumetric water content axis, which would be the intensity for half an hour durations, which is what we chose to use. And then in this space, equivalent intensity volumetric water content axis, we can see that the thresholds are no longer logarithmic, and we have that the thresholds are constant lines in this space, and we can summarize basically any rainfall intensity for its duration, for the equivalent intensity for a given duration for half an hour, because those intensity duration thresholds are based on IDF curves for which we know the equation. So here we have a rainfall event that might trigger a landslide. And what we did is, okay, as I said, we represent this for the half an hour equivalent intensity, and then we can plot it in this space so we can see where it is in this volumetric water content space. And we can draw a threshold which takes into account the volumetric water content to separate between landslide events and landslide no events. And that's what we want to do. So we needed landslide data and no landslide data. And this is the information we were working with. This is the landslide inventory that we had. And it consisted of 603 landslides over Catalonia. Most of these landslides were reported during some significant rainfall events that triggered many landslides. And so, yeah, and we were working with this. So if we plot all these rainfalls that triggered the landslides, which are in blue, and the rainfalls that did not trigger landslides, which are the gray diamonds in the equivalent intensity volumetric water content space. This is how the data looks like. And at the first glance, it's not easy to find those thresholds. But we wanted to find those thresholds. So what we did is we obtained these thresholds heuristically, considering this combination of these volumetric water content equivalent intensity thresholds, rainfall, hydrometeorological hazard, with susceptibility. And what we expected is, and what we can see in this last of the slide, is that we have more landslides when the volumetric water content is low, if the intensity is high. But if we have a higher volumetric water content, we have more landslides, even if the intensity is low. And that's what we expected. So these thresholds, as you can see, are higher if are higher when require higher intensities to be overcome when the volumetric water content is low, and require lower intensities to be overcome when the volumetric water content is high. And here you can see these thresholds, which are the black lines and the different colors, and the white discontinuous lines in this case represent the old rainfall intensity duration thresholds that we used. So we've got these thresholds and we implemented them into the landslide early warning system, and we run it for the period April to October 2020 with both intensity duration thresholds, and then we run it with the equivalent intensity volumetric water content thresholds that we had just obtained. And here is the warning map summary of the landslide early warning system when we run it with the intensity duration thresholds. What we can see here is the number of days with warning that we had obtained. And if you look over if you look over the northeast of Catalonia, close to the border with France, we can see that there are quite a lot of days with landslides. Technically, it's up to more than 30 days with landslides in some sub-basins. But if we look, when we run it with the equivalent intensity volumetric water content thresholds, we see that the number of days for which we predicted landslides were possible are much less. So in this sense, we're saying, okay, these thresholds seem promising and they help us reducing the number of days for which we give warnings. And this was one of the first times in which such kind of thresholds were implemented into a landslide early warning system at a regional scale in real time. Then the performance at a regional scale was challenging. So what we did is this analysis, more qualitative. If we looked month by month, we see that the month of June, that was raining a lot. We thought, okay, why did we get so many warnings on the overall period? So if we looked at the month of June, we can see that we had important rainfalls, accumulations in the northeast, and also the volumetric water content was quite high. Oh, this is actually, then if we look at the output with the intensity duration thresholds, we can see that we had some days with more than 9 days with warning in some sub-basins here in the area where it rained more and the volumetric water content conditions were highest. And if we look at the outputs of the landslide early warning system for the month of June, we see that in that area, there were fewer days with warnings, up to 3 to 5 days. So we decreased the number of days with warnings, as I said, quite a lot. But this is not very quantitative verification. So what we did, because we needed more data and we had already used almost all the inventory for the obtention of those thresholds. So what we did is picking up some events for that were even more recent and which we had not used for the calibration of the landslide early warning system, hydrometeorological thresholds. And then we checked if we were making any improvement in this period from April to October 2020. And this is here I'll show you a case, the case of the landslide in Vegas. which is indicated in the susceptibility map in the left-hand side of the slide as A. And here we had a landslide, well, a debris flow that occurred the 21st of April 2020. It was a day with an important rainfall event, quite extreme. And yeah, there was this debris flow. It blocked the road for several hours, I think days even. And it was a problem because there were some municipalities that were in the other side of the road, which was not able to use. So we looked at here we have the rainfall time series from April to December 2020 in blue, and in orange we have the volumetric water content time series from April to December. And what we see here in the color bar is the warning time series using the intensity duration thresholds. And as we can see, when the rainfall, the 21st of April, here, when the landslide occurred, the rainfall that was observed was quite high, and also the volumetric water conditions were high. So with such rainfall intensities, we could predict using the intensity duration thresholds that a landslide would occur. But here is what we get when we run, and then we run it with the hydrometeorological thresholds, and we see the warning time series using these hydrometeorological thresholds. And we see that we also could predict, because the volumetric water conditions were also high, a landslide on that date. But if we looked at, so here we have a true positive. If we look at other September 2026, we see that, 2020, we see that there was a day for which the rainfall intensity was not as high and the volumetric water content was not as high. But with the intensity duration thresholds, we would issue a warning moderate. And with the hydrometeorological thresholds, we would not issue a moderate warning. We would say that the that the landslide possibility of landslides is low. And then another day in December, we had another moderate intensity rainfall event. In this case, the volumetric water content in the terrain was a bit higher. And in this case, both intensity duration thresholds and hydrometeorological thresholds combined with susceptibility gave us a moderate warning. So in both cases, we have a false positive because no landslide was observed. And that we did for all the sites that we saw in the previous slide, and we obtained similar results. So in general, we decreased the number of false positives when using these hydrometeorological thresholds, but still we had some. So yeah, this is the conclusions. We implemented a first version of the hydrometeorological thresholds for Catalonia in the landslide early warning system. We developed them and we proposed them. And we used the volumetric water content from the EFAS runs of the least flood model. This is interesting because it's you can get it in real time, and they run it, and it's for whole Europe. So this idea could be applied to other areas. But to make a more in-depth calibration and validation of these hydrometeorological thresholds, we would need even more landslide inventory covering longer periods of time that we did not have. So we were very limited into what we were doing to verify that the landslide early warning system was getting the results with these new thresholds. But still, that was one of the first times anyone tried to use such thresholds, and we think it was quite successful and promising. And if you want to know more, it's all published in a paper in Landslides, so you can just scan this QR code and read more about it. That's it. Thank you for your attention.